Okay, welcome back. So we're continuing. Class is over, obviously, but I wanted to finish going through these exercises just so you can refer to them and the solutions as you're working on the homework together. So we left off here, section 2.4, transformations of variables and subsetting of data. The transformations are not particularly new, I don't think, because we already went over, for example, how you would do a log transformation earlier. That said, if you want to create a new variable as a function of an old one, so a calculated variable in your data set, I can show you how to do that. So this is 2.4 question 1. So again, recall that our Cherry data has these three variables. What we're going to do, we're going to add a new variable, which is the log of volume. Actually, we'll create two new variables here, the log of volume and the log of girth. Okay, they're going to become two new columns in the data set. So the way I do that, so I'm going to create a comment here, question 2.4, number 1. And what I'm doing, I'm saying Cherry. Well, I wrote Cherry 5 here, so let's go with that. Cherry 5 is going to be equal to a transformed version of the Cherry data set. So transform is the name of the function. And the first argument I need to give it is the input data set, Cherry. And then tell it what new variables, transform variables, to add. So we're going to add log volume. We're saying log volume is equal to the log function applied to the volume column. Similarly, log girth is equal to the log of the girth variable. Okay, so I'm going to run this command, right? And so we should see in our environment window a new data set, Cherry 5, here it is. And notice it's now 5 variables instead of 3. So we have our original 3, and then we also now have log of volume and log of girth as two new variables in that data set. Right, so I can view it. If you want to see it yourself, you don't trust me, here they are, right? So log volume is the logged values of the volume column. So log of 10.3, for example, is 2.33, and the log of the girth column is here. Okay. That's one way you can add new columns. You can transform your data. Another way you can do that is recall that the way we index or refer to a column in a data frame is using the $sign. So I can actually use that to implicitly create a new feature, a new variable. So one way of doing that, I can say Cherry, original Cherry data set this time, $sign. We're going to create a new variable. We're going to call it volume minus girth. And that's going to be equal to Cherry volume minus Cherry girth. So what this is saying is I'm indexing a column that doesn't exist yet. When I do that though, and I populate a value, in this case volume minus girth, R figures out that it's supposed to create a new column named volume minus girth and fill it with these values. So let's try running this. Right, and you see, remember we did this in the original Cherry data set. So if I go back to the Cherry data set, here we have volume is 10.3, girth is 8.3, volume minus girth is 2. And it created this new column. Right here it is, our new column. And it's entitled volume minus girth. Okay. So that's another way you can create a new column in a data set or a new variable, and that's more commonly, that approach is more commonly used actually. Right, but you can do it either way. However you remember it is fine. So again, we can apply some standard commands to these new data sets. So I can say here in the instructions we're calling the histogram function on the log volume variable. So let's try that. Hist Cherry 5 log of volume. Okay, when I run that, it creates my histogram in the bottom right. Notice taking a logarithm gives you a normal distribution as opposed to right? This is what the volume data looked like originally. This is one reason we often make use of logarithms. They're a useful transformation for taking data that looks like this, where there's a lot of low values and not very many high values. It's also called a long tail distribution or an exponential distribution. When you take the logarithm of data that looks like this, you often end up with data that looks like this, a normal distribution, like a bell curve. Yeah, there's a number of reasons you might want to do that, but anyway, that's often why we use logarithms, is to make our data look like that. Okay, the next question, oh, I'm trying to make a comment. Remember the comment is the hash symbol. Question 2.42 is about subsetting data and indexing a data frame. So identifying columns or rows that I care about from a data frame. So what I'm going to do is I'm going to start off. So this first command, cherry 3, nothing as the indices. If I leave an index blank, that means return all the rows or all the columns. Okay. So remember, for a data frame, when I'm passing indices, I need to give two values that are comma separated in the square brackets. The first value is the rows. The second value is the columns. So cherry 3, nothing is asking R to return the third row, all columns. Right, and this is what it does. So this is the third row in that data set. The girth, the height, the volume, and we calculated volume minus girth earlier. So the one tree, the third tree in the data set. I could also try the head command on this, as we used before. So if I say head of cherry 5, it's going to give me the first 5 rows of that data set. Sorry, excuse me, it gives the first 6 rows. And then I already showed you the plot command. Now, another, by the way, just a side note, log without any base specified. So if you just say log as opposed to log 2, log 10, etc. Log, implicitly, it's log E, or Euler's number, which is the natural logarithm. Okay, it's also known as a ln function. So this is how we get the third row. I can also, sorry, I skipped back there for a second by accident. If I wanted to get multiple rows, that's what's happening here next. So 3 through 5, this is going to give back rows 3, 4, and 5, all columns. Right. And then, as before, I can use complements. So I can say, give me everything except this. That's what the minus sign implies. So I can say minus 3 through 5. So every column, or sorry, rather, every row that is not in 3 through 5. Ooh, it doesn't like it when I do that. So I actually have to say specify it like this. The syntax is important, obviously. So I can put a minus sign and then give it a list of values, right? So it gives me back all of the results except rows 3, 4, and 5. Those are dropped. So notice row 3, or sorry, where am I? So I'm working with the cherry data set. So if we view cherry, notice what it gave us back is 8.3 and 8.6. So the first two values are here. 3, 4, and 5 were omitted because that's what I asked it to do. And then now we have 10.8. So the sixth value is the next one that comes. Right? So it's dropped 3, 4, and 5, rows 3, 4, and 5. Now I think I could do what I wanted, say sequence 3 to 5. And I could say omit that. Yep, right. That's the same thing, right? Because remember, the sequence command gives you, by default, integers between the starting and the ending value. You pass it as arguments, so 3, 4, and 5. The output is a list of those values. So I can use that as well. And I can also, I mean, this is one way of getting the data that I want. It's kind of cumbersome, typically when I'm going to try and pull out rows from my data set, so get subsets of the data, it's going to be based on some conditions, right? Like I only want female customers, or I only want customers who live in, Madrid or something. So what I would do is I would actually use the subset command to accomplish that more easily, where I pass it inputs of 1, what's the data set that I want a subset, and 2, what is the logical condition that needs to be met for me to retain an observation as part of the new data set. So here we're saying subset the cherry data set and keep only trees where the height was greater than 70. Right, so I can say subset cherry where height greater than 70. Okay, it gives me back those values. If I wanted to store that subset of data in a new data frame, I could call it cherry subset, for example. And now the output of this command, which is what we've just seen populated here, is going to be stored into this new data frame called cherry underscore subset. Okay, and here it is in the top right. Right, so it excluded a bunch of observations that didn't meet the logical condition. So where this wasn't true, those observations were dropped. So we see that cherry subset is a smaller data set. We lost 6 observations, right? It went from 31 to 25. There's various examples here of different logical conditions. So subset cherry such that height is 80 exactly, right? We get back 5 observations where that's true. And we can say, as an additional argument, subset cherry such that height is equal to 80, and there's a third option here, select, which says give me back the following list of columns. Okay, and we're saying I want girth and volume. Don't give me back all 3 columns, just give me these 2 for the resulting observations. Okay, and all we get is girth and volume. Okay, if you want to know more about how to use the subset command, certainly you can look at the help file, right, using the question mark to get there. Lastly, what I will mention, if you want multiple conditions to be jointly true, so you can use and, so this is true and that is true at the same time, or you can use or conditions. This is true or that is true. The symbols for that are the ampersand for an and a pipe for an or. So, for example, if I want just observations where height is greater than 70 and girth is less than 15, I would do it like this with an ampersand. So both of these things need to be true for an observation to be kept. Okay, and if I wanted it to be an or condition, so give me the subset where height is greater than 70, or this is the pipe. Okay, on an English keyboard, it is Shift and the backslash, the button right above your Enter key. It may be somewhere else for you if your keyboard is not an English keyboard. Essentially, it's just a long vertical line. So we want height is greater than 70 or girth is less than 15. Right, and this is a bigger data set. Right, notice the last command where I had 2 things had to jointly be true. I got back 17 rows of the 4 variables. This time I said one or the other, so it's sort of a weaker condition, and we got 31 observations back that meet that condition. Okay. So here's a homework question for you. I'm asking you, recover the subset of data from cherry where height is less than 80 and girth is less than 15. Right, so these things have to be true at the same time. Okay, now we're going to move on to merging data sets. So to demonstrate this, I'm actually going to create 2 new data frames first. So here we're working on question 2.51. I'm just going to save my script here just so I don't lose my work. As an aside, if you want to clear your console so it's not full of text, that's not super important, but in case you want to do that, the way you do that, put the cursor on the console and click there, right? And then Control L will wipe the console clean. If you want to wipe your memory, the working memory, you would use this broom. It'll wipe out all the variables in memory. They won't be there anymore. Similarly, I can clear a plot down here with the broom. I'm going to leave these here. I wouldn't click that at the moment because we may use some of these in a second. Okay. So question 2.5-1. First thing we're doing is creating a new data set. So I'm going to say new data, and it will contain a data frame comprised of girth values 11.5 and 17.0, and height values equal to a list of 71 and 75. And then we will create, it'll have volume values equal to 22 and 40. Right. Actually, there's a typo here. This is showing up on the same line, but actually we're going to run that after this command to see what the data frame looks like. So this is the whole command here. I'm going to run this. Okay. And essentially what I just did, this new data that I just built, I created a data frame of 2 observations with the same 3 variables. Right? Girth, height, and volume. Actually, it's notable that I added this column here previously when I was just showing you a way of creating a new column. So what I'm going to do, before I move forward, I'm actually going to get rid of this extra column because it may cause me headaches in a second. Because what I'm about to do is to try and merge this new data, these 2 new observations, into the existing Cherry data. But notice I only have 3 variables here in the new data and 4 up here. And this misalignment can create a headache. So what I'm going to do is I'm going to create, and I'm going to overwrite the Cherry data set with itself, all rows, but only the first 3 columns. Okay, so I can use sequence to do that, columns 1, 2, and 3, or I could say minus column 4. Actually, I think it may require me to. That worked, right? So here we have Cherry. It's only the first 3 columns are now there. It deleted the 4th one when I did that. I overwrote it with itself minus its 4th column. So now both data sets have 3 variables, girth, height, volume, girth, height, volume. So now I should be okay to merge these 2 things together. So what I'm going to do, I'm going to say a new data set. It's called all data. And what I'm doing is using the rbind command, R-B-I-N-D. That means bind rows together. Okay, so we have one data set, which is 31 rows of cherry tree data, and then we have the new one we just created, which is 2 new trees we found out about. And we want to bind the 2 new rows onto the bottom of the 31 rows that we already have. So using rbind, we are going to bind the cherry data set with the new data we just created. Okay, and that gives us a new observation here, or a new variable, data frame called all data, and notice it's now 33 observations. So we had cherry, which was 31, and we added on 2 more, the new data, and that created our new data set. And I can print it on the console if we want, or I can view it on the top left window if we want. Okay, here it is. Right, so that's one way of merging. Okay. Now, we can also add new columns using the cbind command. So I showed you earlier 2 ways that we could create a new column. So one was the transformation function, so transform, where it was a new calculated variable. Another way to do it is using the $ index and just using it to index a column that doesn't exist yet, and then populating some values into there based on some calculation. Right, so maybe in what we showed you before, I showed you how to add the log of volume as a new variable in the data set, a new column. I showed you how to do volume minus girth as a new variable. So that's another way of doing that, is to first create the new column and then use the cbind command, column bind. Right, so we have our data set, and we're going to bind that data set with an additional column. It works the same way as the rbind command. It's just we're binding in a column now instead of a new row. So first I'm going to create the relevant column. In this case, we're calling it precipitation. And we're saying that's going to be a vector which is comprised of a random normal draw of 31 values. So we're drawing from the normal distribution at random, where that normal distribution is defined with an average value of 50 and a standard deviation of 10. Okay, so it's essentially saying We have an assumed distribution with an average value of 50, a standard deviation of 10. We're going to, from that distribution, draw 31 random values and stick them into a new vector. Right, so I'm basically simulating some fake precipitation data. What does it look like? There it is. And we're going to bind that data into our Cherry data set. So we have 31 observations. We made that many on purpose, right? So it lines up in terms of the dimensions. 31 values that are going to go to our 31 trees in the Cherry data. So we're going to get there by saying, make a new data frame called all data 2, and we're going to use column bind the Cherry data set with the precipitation vector we just created. Okay, and here's all data 2, and it's 4 variables now. It's got the 3 that were already there in the Cherry data, and we've added a new column, which is precipitation. So how much rain fell on that tree. All right. Now, 2.6, these are all homework questions. So essentially, you're going to reuse a lot of the things I've already shown you in this lab. You're going to import an Excel spreadsheet called Tomatoes. It's about tomato data. And your goal is to accomplish the various tasks that are described here in section 2.6. Right? Again, remember to be populating your answers into a script. And again, I really encourage you to create a Word document where you walk through, you can paste in examples of code, screenshots of the output that you got on the R console, running the different things, just so it's clear to me that you did it properly and you knew what you were doing. Okay. So I'm going to skip that because I'm not answering that for you. You need to work on that as part of the homework assignment. And I'm going to complete this lab just going through some very basic plots. And we've already seen a few of these actually. So this should be quick. So 3.1, question 3.1. So the first thing we're going to do is work with the Cherry data set again, right? And what we're going to do, let's just try plotting that data. So plot is the function, and I pass it the Cherry data frame as the argument, and it'll create a plot in the bottom right window. There it is, right? So we saw this earlier. It's a scatter plot it creates. Recall the x-axis here is, in this case, girth. The y-axis is height. So we have one tree that had a height of roughly 67, and the girth was 8 point something. That's what this data point represents, right? So every dot is an observation of the data set. What else can we do here? We can plot 2 specific columns. So I can say plot Cherry volume against Cherry girth. And it'll do just that scatter plot with those 2 specific variables, right? Every dot is a tree. We see something that looks like a linear relationship, which is not surprising. So the wider the radius of the tree, there's a linear increase in the volume of the tree as that happens. And that's just based on the function that defines volume. Okay, I can also plot their logarithms against one another. So the log of Cherry volume and the log of Cherry girth as x and y coordinates, right? And yep, those are also linearly related, not surprising. Okay, and then if I just pass one variable, in this case Cherry's height column, right? It only has one variable, so again it guesses how should I plot this. And it decides to provide a univariate scatter plot, which is kind of ugly, right? So what it's doing is it's essentially plotting height against what's my index in the data frame. This isn't a very meaningful value, right? It's just showing you as you go down the list of observations, what's the height of each tree. That might not be what you want, right? So it doesn't always guess the best, right? Its default choice for how to plot data is not always ideal for representing information. So in this case, we might actually want a histogram. Histograms tend to be the mode of choice for plotting univariate data or single variable data. Right, again, it's a density distribution. I've shown you this earlier. it tells you how common are certain values in the data relative to others. So we see it's rare to have anything above 85 or below 70, and most trees are between 70 and 85 in height. Another thing I can use instead of a histogram, which is good for plotting density distributions of variables, is the box plot. Right, so box plot is the name of the function. If I run this, this is a box plot. It's hard to read by default here in this window, but if I click on the zoom option, now I can take this window and blow it up. Okay, this is the distribution. So the way you read a box plot, the solid line here is the median. The top of the box is the third quartile, right? So the 75th percentile. The bottom of the box is the 25th percentile. This lower bar is the minimum. This upper bar is the maximum. And if you have outliers in the data set, they're actually mathematically identified based on some criteria, and they'll show up as dots outside of the min and the max. So a box plot is another way we can plot univariate data. Okay, now we're going to do some bar plots. A histogram is actually a type of bar plot. So let's just make a new vector. We're going to call it temp, short for temperature. It's a list of numeric values, 65.5, 79.1, 83.9, 84.0, and 76.9. What happened? Oh, I missed a comma. There we go. And now bar plot of the temp variable. If I don't pass it a names argument, it's not going to have any labels on the x-axis. All it did was show, so each bar is each unique value. There's 5 of them, 1, 2, 3, 4, 5. The y-axis is what is the value. Okay. If I wanted to have names under each of these bars, I could say bar plot temp, and the names are going to be equal to whatever you want actually. So I'll put x, A, B, C, D, and E. Right, and now we have names on our bars. I could call them anything I like. Okay, there are other options obviously for plots, and it can get much more complicated and much richer with visualizations. We're going to come back to that hopefully if we have time at the end of the course. But that's it for now for your lab. So just a final note, I really want you to go back and read the instructions at the beginning of this document, because it states quite clearly what the expected deliverables are for your homework submission. Again, you should work with there should be no more than 2 to 3 students in every group. And you make sure, again, I encourage you to write a Word document as your submission file. And at the beginning, have a title page and put the names of the students that participated in that submission on the front of it so that I know, and so you know you get a grade. Okay. If you have any questions as you're going along, you can shoot me an email, you can message me on Slack, and I'm happy to help you out. Or feel free to talk to your colleagues in the course. Thank you very much.